sacred institutions. Bedroom eyes, they called them in a bygone day.
Hello, and welcome to Physical Attraction, the show that explains physics, one chat-up line at a time.
But for corrupting others to a life of carnal pleasures and lewd designs. A man whose erotic desires and libertine practices are used to titillate the unsuspecting and would stoop to any depth.
Hello, and welcome to Physical Attraction. Coming up, we have two episodes on two subjects. One of them sounds amazing, but is actually much more mundane than all that. And the other one sounds mundane, but is actually pretty amazing. But in time-honoured physical attraction fashion, I'm going to start some way off the beginning, and then find my way to the starting line. In Paris, city of light, city of love, city of clichés, you can visit all kinds of places. You can visit the Eiffel Tower, which commemorates the anniversary of the French Revolution. Robespierre and many of the others involved in that conflict had a dream that, when they overthrew the Ancien Regime, that creaking power structure that had dominated and oppressed France for so long, that they would bring in a new age of rationality and intellectual enlightenment. But like so much in the French Revolution, the good sentiment that reason will prevail devolved into madness and chaos. If you're being charitable to the revolutionaries, you can say that they were ahead of their time, that they rejected the dogma of the Catholic Church that had prevailed for over 1,000 years. But in 1793 struggled to find an alternative worldview to put in its place, and struggled to find a population ready to accept that new worldview. But if you're being more reasonable, you can say that this devotion to rationality, like the revolution itself, struggled under the weight of its own internal contradictions. Who gets to define what is and isn't irrational? Who sets the standards? So it was that you ended up with the almost oxymoronic and violently atheistic cult of reason, which encouraged people to worship and venerate ideals such as truth, virtue, and reason in place of the old deities. And this then degenerated further into Robespierre's cult of the supreme being, which tried to restore God without the power of the Catholic Church. The cult of the supreme being, along with Robespierre and Saint-Just's tendency to centralise control in a tiny, undemocratic committee for public safety, and execute an awful lot of people during the Great Terror, led in part to the downfall of this first iteration of the French Revolution. A few years and a few political convulsions later, and this would lead to the rise of Napoleon, and he left his mark in the city in the form of an imperial arch in the old Roman style, to celebrate his military victories, the Arc de Triomphe. Yet there is another legacy of the French Revolution's push for rationality that you can find in Paris. If you go to the Musée des Arts et Métiers, you can see all kinds of things. A supercomputer from 1985, which now has less raw processing power than a couple of mobile phones. A hilarious pair of binoculars from the 17th century, which got around the tricky focusing on faraway objects problem by being so long that no object is truly far away from them. Then there's the Avion 3, an early attempt at an aircraft shaped like a bat and powered by steam. This is what people write about it. The first flight was attempted on the 14th of October, and most sources agree ended almost immediately in a crash without ever leaving the ground. Later in his life, the inventor claimed that there had been a flight of 100 metres on this day, and he said that he had 2 witnesses to confirm it. Whatever actually happened, the French military was unimpressed with the demonstration, and cancelled any further funding. But alongside all the failed aircraft and magical, ridiculous binoculars, in this museum there's a lump of metal. Okay, to be more precise, a bar of a special alloy, 90% platinum and 10% iridium, that is almost exactly 1 metre long. The almost exactly part is a fairly new innovation because up until 1960 it was exactly a metre. Not to the nearest millimetre, or the nearest micrometre. This bar was exactly 1 metre long because this bar defined what the length of a metre was. A metre was the length of this bar. From 1799 right the way up until 1960, the answer to the question, how long is a metre, is pointing at some metal bar and saying, it's the length of this bar. It might seem a little arbitrary, but in a lot of ways, units are just something that we all agree upon. They are yardsticks for describing the world. The idea of a day we can all sort of comprehend. After all, it defines when the Earth rotates on its axis. It's the cycle by which things get light and dark again. Once a day you will probably feel an overwhelming urge to go to sleep, and so your conscious experience of the world is divided into these neat little units, ignoring for a minute that if you measure days by light or by sleeps, the length of the day will vary pretty wildly. The Egyptians had 24 hours to the day, although funnily enough they varied in length, keeping 12 for both day and night, so that in the winter, daytime hours were shorter than nighttime hours. But what is an hour? What is a minute? What is a second? These are really just convenient subdivisions, convenient ideas that we have, chosen because it was easy to divide the day up into these lengths of time, and because they correspond to our experience. It's interesting that various ancient civilizations have come up with similar lengths of time, which maybe implies that the speed of clocks is somewhat related to the clock speed of the processor in our own heads. The Babylonian second was 3.5 of our seconds. You could say that the second is about the length of a thought. It's about the length of a heartbeat, our own internal, pulsing, irregular clocks. Those strange timekeepers of mortality, the heartbeat, dependent, in a very non-linear way, on physical and emotional intensity, beating faster, passing time faster, when you're at your most alive. As if to remind you that, regardless of our attempts to label it and put it in little constant boxes marked rational and scientific, the human perception of time is slippery and far more dependent on our emotions and our psychology than we'd like to think. Things were much worse, of course, in the days before we started arbitrarily labelling and pinning down definitions about what a second was and what a good unit of length was. Previous definitions had been pretty ridiculous, and if you think about it, a failure to agree on a unit of length universally is a pretty big deal. If I promise you 200 metres of cloth and I give you 200 of my metres, but it's only 190 of your metres, you're going to feel ripped off. And don't even get me started on the foot. Henry VIII reportedly tried to define a foot in terms of his own height, while in the 16th century, the procedure, honestly, for determining the length of a foot was to literally grab 16 random people from your church on Sunday, line them all up foot to foot, and then divide that length by 16. I wish I was kidding about that, but that's how they did it. So the French revolutionaries might seem a little obsessive with their incredibly carefully measured bar, but they had a point. Of course, in many ways, physics doesn't care about units. You could repeat the calculations of physics, measuring lengths in units based on your own height, and temperatures based on your own body heat. Again, that might sound silly, but I should remind American listeners from our thermodynamics episodes that this is part of what the Fahrenheit scale is actually based on, the body heat of Fahrenheit. And physicists regularly do work in units that are convenient for the particular situation. So, for example, we've previously talked about particle physicists using the electron volt as a unit of energy, and they often talk about masses in terms of energies as well, using them interchangeably. You'll regularly hear them say that the mass of an electron is around half an MeV, which doesn't make an awful lot of sense unless you know that E equals mc squared holds, because an MeV is in fact a measurement of energy rather than a measurement of mass. The unit size is convenient because it's saying that 9.11 times 10 to the minus 31 kilograms, that's the mass of an electron in kilograms, but it's cumbersome and difficult to remember, and it makes most of your numbers unreasonably small. So there's nothing special about the meter and the metric system. The initial attempt by those radical French revolutionaries to institute the metric system, and some kind of universal adherence to truth and logic, it didn't quite catch on. They had the right idea, standard measurements of length, time and mass in the meter, second and the kilogram, but they took things a little too far. There was a chaotic rollout of a sort of decimalised calendar. Alongside famously declaring the first year of the revolution to be year zero of a new calendar, and renaming all of the months after the weather they were associated with that month, there was even an attempt to introduce decimalised time. They kept 12 months, but they were 30 days each and divided into 3 weeks of 10 days. The day was divided into 10 hours of 100 minutes of 100 seconds. And as you can probably figure out, that never caught on. So after the Committee of Public Safety had their political downfall, and Robespierre himself actually managed to botch his own suicide and end up with the far more poetic fate of being guillotined after having guillotined so many other people, the French authorities later quietly discarded a lot of the nonsense that had been suggested, and quietly kept some of the stuff that made a little more sense. The meter was defined by this prototype meter, the metal bar. The kilogram, which was based on the mass of a certain volume of water, was a small block of platinum manufactured specifically to define the kilogram. And that would remain the definition of the kilogram and the meter for over a century. They use platinum because it doesn't corrode. The issue, of course, is that, well, no length is really constant. Changes in temperature cause metals to expand and contract, for example. There are small accumulations of dust sometimes on the end of the metal parts. And even your height isn't constant. If you spend a lot of time standing or sitting up, you will end up being shorter at the end of the day than you were at the beginning. The scientists quickly realised this, and so if you ever want to retrieve and precisely measure that 1 kilogram, you have to do it at a certain temperature and pressure. They use platinum because it's not reactive, and it doesn't expand by very much when temperatures change. But eventually, defining the length of a metre by a stick of metal in some lab somewhere wasn't constant enough. For a while, they defined it using something that everyone could hope to agree on: the emission lines from krypton gas. You'll remember that when atoms get excited, energy is transferred to their electrons. They can de-excite and lose that energy by emitting photons. It's this that causes those beautiful glowing clouds of gas in outer space that you might have seen pretty pictures of. The gas gets heated up, and depending on what it's made of, the atoms de-excite with different wavelengths, producing different colours. Every atom of the same isotope of an element is the same, and under the same conditions, it will emit radiation of the same wavelength. So they picked the orange line of krypton because it's nice and bright and visible. And for a while they said the metre is some multiple of the wavelength of this orange line of krypton. But then this began to suffer in a way to other standard measurements because, after all, what is a measurement? Any good measurement has some uncertainty. You don't know precisely the value. If you measure your height with a tape measure, it might be to the nearest centimetre, or even millimetre, but below that you're uncertain, you don't know. And really it's the same with any measurement, even if it's only billionths of metres that you're unsure about. The problem was that, as we kept pushing at that uncertainty limit, suddenly it became clear that what we were using wasn't ideal. We discovered that the bars of metal were changing too much. We worked out that the line for krypton was slightly asymmetrical, so you'd have to pick a point to measure for consistency and so on. Eventually, because time could be measured more accurately than light, they defined the metre with the current definition that it now has, which is in terms of the speed of light in the vacuum, which, as far as we know, is one of the few fundamental constants built into the structure of the universe, and the unit of time, the second. So now, at long last, the metre is officially, quote, the length of path travelled by light in vacuum during a time interval of 1 divided by 299,792,458 of a second. About time, then. Time was at first the hardest to measure. People tried to make things nice and consistent by measuring things in terms of fractions of a year, or of a day, but years and days aren't as solid and immutable as you'd like to think. We're constantly putting in leap days and leap seconds to correct for our years getting out of sync with the rotation of the Earth. And what's more, because of the tidal drag on the oceans, the Earth's rate of rotation is gradually slowing down. The Moon, through its drag on the oceans, is gradually shifting the length of a day to be closer to that of a lunar month. It'll keep going until they're both 47 days long. But long before you have to worry about your Monday lasting for weeks, we'll all be dead, because we only gain 2.3 milliseconds on the day every century. You might think, after listening to the Teotwalki specials where we detailed all of the various threats to human civilization over the next century, that days getting a few milliseconds longer is a pretty tiny consideration to think about. But I think that it's both important and cute that someone somewhere in a dusty room is keeping track of this kind of thing for us, the 2.3 milliseconds per century drift on the length of the day. So measuring time. The first clocks relied on things like sundials, burning candles of a certain length, or mechanical processes that require constant winding and slow down over time, so none of these was particularly ideal either. Anyway, it was soon realised that the atomic decays offer the most accurate possible, the most consistent possible measurements of time, and it's using atomic clocks that some of the most accurate measurements can be determined for time units, which get converted into a second. Ideally, the clock is as close to absolute zero as possible when this decay is measured, because any energy can change the rate of the decay, and it's currently determined by a transition in what's called the hyperfine energy levels of cadmium. By the way, this is our physics-based chat-up line for today. Maybe I'd better include both the spin-orbit coupling and the electron-nuclear spin interaction in a consideration of your energy levels, because you're not just fine, you're hyperfine. Yeah, I know, one day all of that deserves explanation, but not today. Not while we're talking about time. Out of the first 3 units to be defined in the international system, it's actually only mass, only the kilogram, that is still defined by a lump of metal in a vault somewhere. Which is a little crazy, I know. You'd think it would be some multiple of the mass of the electron now, but that's not how they do it. It's still defined by the International Prototype Kilogram, and it's made out of 90% platinum, 10% iridium. What's even crazier is the security precautions around this thing. It's in a locked vault, kept in filtered air at a constant temperature and pressure. It's taken out and carefully remeasured every 40 years to ensure that the value of the kilogram remains consistent. It requires 3 separate keys, presumably wielded by stern and serious-looking agents of science, who will only reveal their name, rank and serial number if questioned. There are 6 identical sister copies, in case we lose 5 of them. All of this feels a little bit like they're making up for the embarrassment of having to deal with the fact that our definition of a kilogram, our definition of the fundamental unit of mass, comes from a lump of metal, and nothing more fundamental than that. But when you're trying to be this precise, weighing the thing and getting a kilogram isn't enough. You need to be sure that the gravitational field is the same every time you weigh it. It's that sensitive. I'm going to spare you the literally pages and pages and pages of documents produced by what I can only describe as some of the nerdiest nerds to ever have nerded, who are lobbying for their own pet measurement systems to take over from this lump of Parisian metal. Suffice it to say that people have demonstrated that the lump is gradually changing in mass by millionths of a gram, mostly due to things accumulating on the surface which can't be cleaned away. They will rant about how it is an embarrassment to science and should be melted at the stake. You can see very lengthy, detailed explanations of why we should be using, say, magnetic forces, or the masses of a certain number of atoms, or so on, to define the kilogram. And one day we probably will, and the IPK, the International Prototype Kilogram, will be consigned to a museum somewhere, and eventually forgotten about as some quirk of history. But for the moment it has its time in the sun, although preferably not for too long, or the mass might change. All masses, all forces are defined through me, says the lump of metal. Fear me. I am not just any old lump. I am a lump of metal that weighs exactly 1 kilogram. So we have these units then, the metre, the kilogram and the second, that are all SI base units. SI is for the System International, which, as you can see, has some heritage in its French Revolutionary past. And these are mostly the only ones you need, because you can derive most of the other units from them, which are called the SI derived units. So for example, we know that force is mass times acceleration, so we can define force as mass times length divided by time squared. That's how 1 Newton of force is defined. It's the force needed to cause 1 kilogram of mass to accelerate by 1 metre per second per second. Similarly, energy is a force multiplied by distance. So a joule of energy is the energy you get by applying a force of 1 Newton over a distance of 1 metre. You can derive things like the Pascal for pressure in a similar way. But since they can be derived from the other units, they aren't base units. Of course, as we learnt more about electromagnetism, it was clear that there were more things to be measured than just mass, length and time. There was this thing called electrical charge for a start that clearly needed some units. The trouble is that measuring electrical charge turned out to be exceedingly difficult. You might think it would be easy, you just measure the forces, but measuring static charges, the currents that aren't moving, is far less easy than measuring currents. The unit of current, the ampere, was relatively easy to measure. It's actually a little strange as it's currently defined as, quote, the amount of current that needs to flow in parallel wires separated by a metre to produce 2 times 10 to the minus 7 newtons of force. So you can see that they defined it in terms of the experimental setup, and that's how it was originally measured. Because currents turned out to be much easier to measure than charges, in SI, charge is actually a derived unit. 1 coulomb is the amount of charge that flows past a point where a 1 amp current flows for 1 second. From the ampere, then, you can get charge, electric field, magnetic field, and stuff like that when you combine it with the other SI base units. And this is odd in some ways, because nature does in fact have a fundamental unit of charge, in a way that in some ways it doesn't seem to have a fundamental unit of length, or a fundamental unit of time. The fundamental unit of charge appears to be the charge on the electron. We don't see any subatomic particles that aren't multiples of the charge on the electron. Even quarks, which can never be separated from the nucleus, are still only exactly 1/3 or 2/3 the charge on the electron. So nature has this well-defined unit of charge then, but it's tiny. However, the coulomb is a very big unit of charge. Lightning strikes, which seem about as dramatic an electrical event as we can imagine on Earth, only result in transferring about 15 coulombs of charge. and you need around 10 million billion electrons to get up to a coulomb of charge. But I suppose one or other of the units has to be either tiny or ridiculously large. Similarly, it means that the magnetic field unit, the Tesla, calm down Elon Musk fans, well, the Tesla is a little large for our usual scales. The Earth's magnetic field has to be measured in microtesla, your fridge magnet's magnetic field in mini Tesla, and the strongest steady magnetic field humans have ever produced is around 45 Tesla. On the other hand, 16 Tesla was enough to levitate a frog, literally due to diamagnetism in the water of the frog. The same calculations indicate that 50 Tesla should be enough to levitate a human, but it's not that simple, because the only reason that the frog levitates is that there's a huge magnetic field gradient. This is what determines the force. So you'd need to create a magnetic field that's 50 Tesla at your feet and 0 Tesla at your head, which is an insanely difficult engineering problem. And that would be enough to change the water in your cells into little diamagnets that would be repelled by the magnetic field, allowing you to levitate in the air. But amazingly, at least if frogs are anything to go by, you might not be harmed this much by that magnetic field gradient, as long as it's sufficiently smooth that different parts of your body aren't being pulled apart. I would say don't try this at home, but I don't think anyone at home is going to have access to a 50 Tesla magnet. And if they do, they probably also have access to liquid nitrogen and all kinds of cool stuff like that. So I'm going to let them try whatever they want. It doesn't end with the ampere though. There are also base units, including the mole, which is really just a number that determines the amount of a substance, the Kelvin absolute scale of temperature, which we discussed pretty thoroughly in the thermodynamics episodes, and the candela. The candela is a little weird. It's defined as the luminous intensity in a given direction of a source that emits monochromatic radiation of a particular frequency that has a radiant intensity in that direction of 1/683 watts per steradian, which is an incredibly complicated definition that has not one but two constant values in it. In non-gobbledygook, what the candela measures is how bright things appear, and that's why they choose radiation that's monochromatic at a particular frequency. It's the frequency that humans are most sensitive to in our eyes. So the candela, as the name suggests, is kind of a formalised version of the luminous intensity of a single candle. Now you're probably thinking, as I did for a long time, that couldn't we derive something similar in terms of, say, energy and time? Something like how much energy from the source emerges at a particular angle at a particular time. That kind of thing. And then you wouldn't need another base unit at all. You could just derive some version of luminous intensity from all of the others. Well, yes, we could. That's called the luminosity, and that's what physicists use, for example, in talking about stars. But this sense of intensity is intrinsically linked to the human eye and its own sensitivity. So the candela is a little wishy-washy compared to the others, but it's important for industry to have a definition of light in terms of how bright something is. After all, if you were categorising light bulbs and things like that just by luminosity, then things depend on the frequency of the radiation concerned. You could get a light bulb and a radio emitter, or an X-ray emitter, that had the same luminosity, the same energy being produced, but you wouldn't even be able to see the other two. So there's use for some unit of spectral intensity that's actually tuned to human vision, and that's why we're stuck with the candela. So you can see already that around the edges of this system of international units, there are some pretty concerning inconsistencies. The candela is useful, but basing something on human eyesight and how bright candles are seems a little old-fashioned. The Kelvin temperature scale gets a lot of flack too, with some people pointing out that you can derive it just from energy, since after all the temperature is just a measurement of the thermal energy of the body. From another perspective, temperature is just the Lagrange multiplier that emerges from the statistical mechanics approach to maximising entropy. The point is here, although you can technically define a temperature in terms of energy, and you might not need it, talking about temperature is useful enough that it gets its own units. Next episode, we're going to talk about why units are important and what dimensional analysis is, and that is the incredibly cool thing that sounds incredibly uncool that I talked about previously. Thanks for listening to this episode of Physical Attraction. If you've enjoyed it, please visit www.physicspodcast.com, where even if you've not enjoyed it, you can leave commentary with all your questions and concerns. And over on the website www.physicspodcast.com, you will find a donate link where you can donate some money to us if you think that we're doing a good job. Until next time, try not to lose any of the prototype kilograms that define how heavy everything is.
Pornographic tastes, a Marquis de Sade would have regarded as a peer. here's a